Next question. A student set up the circuit shown in the diagram. The student uses the circuit to obtain the data needed to plot a current potential difference graph, so that's just a current voltage graph, for a diode. So you can see there's a switch, a cell, voltmeter, diode, ammeter, variable resistor. Well, you can see straight away that these are in the wrong place. Draw in the boxes the circuit symbols for a diode and the circuit symbol for a variable resistor. Watch this. D, I, O, and that's all you're getting. It's the first three letters of diode, and that is what the symbol for a diode looks like. Variable resistor starts off in life as a resistor. I'll put a V on there for variable and then do my little line through. It's an arrow. It doesn't really matter if the arrow goes up or if it comes down. I like the arrow going down, so then that looks like a V for variable. The student made two mistakes when setting up the circuit. What two mistakes did the student make? Well, you can see straight away they've got the voltmeter connected in series and they've got the ammeter connected in parallel. The voltmeter should be here and the ammeter should be there. Parallel across the diode. After correcting the circuit, the student obtained a set of data and plotted the graph below. So you can see current up the side, potential difference across the bottom. At what potential difference did the diode start to conduct an electric current? Well, the current is 0, until it gets to about 0.2 volts. Use the data from the graph to calculate the resistance of the diode when the potential difference across the diode is 0.3 volts. Use the correct equation from the physics sheet. So we are trying to calculate the resistance when the voltage is that. Now, we've got voltage, we need resistance, and the other thing it gives us is the current. So is there an equation that connects these three things? Yes, there is. It's Ohm's law, which is V equals I times by R, so voltage equals current times by resistance. Now we need to rearrange that, so therefore resistance equals voltage divided by current. Now it tells us it wants the voltage to be 0.3 volts, so from the graph, when the voltage is 0.3, you can see that the current is that. Now that's 0 and that's 0.010, so that'll be 0.08. Sorry, 0.008 amps. I've tried to make it confusing by putting some extra noughts on the front. Be careful. And that equals 37.5 ohms. Next part. The diagram shows the trace produced by an alternating current AC supply on an oscilloscope. So you can see it's going up and down. That's what we would expect an alternating current to do. Each horizontal division on the oscilloscope represents a time of 0.01. So horizontal means going that way. Remember, vertical would be up and down. Calculate the frequency of the AC supply. So frequency equals 1 divided by the time period, where the time period is the time taken for one complete wave. So the time taken for one complete wave, start there, go all the way up, back to the middle, all the way down, back to the middle. That is a complete wave. And how many squares is it? 1, 2, 3, 4 horizontal squares. Each horizontal square represents 0.01. So that's 1 divided by 0.01 times by 4. I could have just put 0.04, of course. And that equals 25 hertz. Next part. A diode is now connected in series with the AC power supply. Okay, so you can see this time, instead of it coming down, it just stays on 0. Where it goes up, it still goes up, but on the part where it should be coming down, it stays on 0. Why does the diode cause the trace on the oscilloscope screen to change? It's worth 2 marks. So a diode does not allow current to flow in the reverse direction, so therefore instead of being a negative value, it's a 0 value. So whenever the current flowed backwards and the trace was originally negative, now it is 0. Next question. The diagram shows the structure of a cable. The cable is part of an under-soil heating circuit inside a large greenhouse. Right, so you've got the insulation around the outside, copper braid acts as an earth wire, and then you've got an actual live wire and an actual neutral wire. And again, those wires are also separated from each other by insulation. The cable is connected to the mains electricity supply through a residual current circuit breaker. So that's just probably a circuit breaker, is what your teacher said. If the cable is accidentally cut, the RCCB, so the circuit breaker, automatically switches the circuit off. What is the frequency of the mains electricity supply in the UK? It's actually 50 hertz. I know we just did a question before and it came out as 25 hertz, but they are well within their rights to try to catch you out. Next question. What happens as the cable is cut to cause the RCCB to switch the circuit off? Well, the current would flow to earth. You could see through the copper braid. The RCCB would detect a difference in the current between the live wire, which takes the current into the appliance, and the neutral wire, which takes the current out of the appliance. So if the currents are the same, the circuit breaker does not switch off. But if the current is different in the live wire compared to the neutral wire, then the circuit breaker thinks, hey, I've lost some current here, there could be a problem, I'd better switch the circuit off. So the RCCB would detect the change between the live and the neutral wire and switch the circuit off. Next question. A circuit can also be switched off by the action of a fuse. Give one advantage of using a circuit breaker to switch off a circuit rather than a fuse. Well, a circuit breaker can simply be reset. Once a fuse has blown, then you've got to replace the fuse. And if you haven't got a replacement fuse, you're going to have to go down to B&Q or somewhere else and buy one, which is a massive inconvenience if it happens at night time. Next part. The 230 volt main electricity supply causes a current of 11 amps to flow through the cable. So that's our voltage, that's our current. Remember, a great exam technique is to write down what you know as you know it. Calculate the amount of charge. So Q, that's charge, that's going to be question mark, that's our target. Calculate the amount of charge that flows through the cable when the cable is switched on for 2 hours, that's our time, and give the unit. Now, the thing is time needs to be in seconds. So 2 hours equals 60 minutes times by 60 seconds, and then obviously times by 2 hours. So that's 7,200 seconds in 2 hours. Use the correct equation from the physics sheet. So calculate the charge. So charge equals current times by time. So we know the current was 11 amps, and we know the time in seconds was 7,200 seconds. Now that is how they'll try to catch you out. They'll expect you to just put the time as 2 hours. So that's 79,200, and they want the units because the unit's not there. Coulombs are the units for charge. Calculate the energy transferred from the cable to the soil in 2 hours. Use the correct equation. So energy is our target. Well, EastEnders equals the Queen Vic. Now I don't watch EastEnders, but I do know that there's a pub there called the Queen Vic, and that's how I remember this equation. So I've just worked out the charge, 79,200 coulombs, and I'll multiply that by the voltage which they gave me before, and that equals 18,216,000. Now you'll notice instead of calling this question C, they've called it question 6B part 2. So that is an indication that whatever you worked out up here for this question is also perhaps needed for the next question. So be careful when they've said a part 1 and a part 2, it all goes together. So there's a tip. C. The heating circuit includes a thermistor. The thermistor is buried in the soil and acts as a thermostat to control the increase in the temperature of the soil. Describe how an increase in the temperature of the soil affects the thermistor. So an increase in temperature, how is it going to affect the thermistor? Well, the thermistor is something that changes its resistance as the temperature changes. So as temperature increases, the resistance of the thermistor decreases, so it allows more current to flow. Remember, we use resistance to control the size of a current. If you've got a big resistance, it only allows a small current to flow, and if you've got a small resistance, then it lets a big current flow. The diagram shows the circuit used to obtain the data needed to plot the current potential difference graph for a filament bulb. So here we go, our standard circuit, ammeter over here, voltmeter across the component, and a variable resistor over there. And we get a current voltage graph that looks like that. Why is the component labelled J included in the circuit? Well, that is so that we can get lots of different currents and lots of different voltages in order for us to plot the graph. The resistance of the bulb increases as the potential difference across the bulb increases. Why? Well, as the voltage increases, the current increases, and so the bulb gets hot. As the bulb gets hot, the atoms or ions start to vibrate more, so there's more collisions. That's what resistance is. The bulb is at full brightness when the potential difference across the bulb is 12 volts. That's our V. The current through the bulb is then 3 amps. Calculate the power. So power equals question mark of the bulb when it's at full brightness, and give the unit. Use the correct equation. So what is the equation that connects these three things? Well, power equals current times by voltage. So that is 3 amps times by 12 volts, and that equals 36. And power is measured in watts. Next part. In this question you will be assessed on using good English, organising information clearly, and using specialist terms where appropriate. The table gives data about 2 types of light bulb people may use in their homes. So we've got a halogen light bulb and a light emitting diode, which is a LED. Tells us how energy efficient they are, tells us the cost of one of those light bulbs, and it tells us the average lifetime in hours of the light bulb, so how long it's going to last. Both types of light bulb produce the same amount of light. Evaluate in terms of cost and energy efficiency the use of the 2 types of light bulbs. To gain full marks, you must compare both types of light bulbs and conclude which light bulb would be the best to use, and it's worth 6 marks. Right, let's just go off the information without analysing anything just yet. So we can see the light emitting diode is the most energy efficient, so we'll pop that in. What you want to avoid is don't just turn around and say the light emitting diode is 32% efficient and the halogen is 10% efficient. Okay, they've gave you that information. What they want you to do is they want you to use that information to make a conclusion. So from this information I can conclude that the LED is the most energy efficient. What about from this information? Well, I can conclude that the halogen bulb is the cheapest. If I was just going into a shop and buying one of them, that's the cheapest. Now the average lifetime in hours, I can see that the LED lasts longer than the halogen. Right, now I've only got 3 things, so I need to start digging around and trying to get my last 3 marks. So if something is more energy efficient, that means it doesn't waste as much energy. So we could say that the LED doesn't waste as much energy as the halogen. Right, let's have a look at this average lifetime. Now that lasts 2,000 hours and that lasts 36,000 hours. So if we let the examiner see what we're doing here, 36,000 hours divided by 2,000 hours, that equals 18. So we would need 18 halogen bulbs in order to last the same amount of time as the LED. Now let's consider the cost of that. So one LED costs £11.70. If we needed 18 halogens, so 18 halogen bulbs would cost 18 times by 195. So that would be £35.10. So I might get a mark for that. Now if we could work out how much cheaper it would be then. So if we do £35.10, take away £11.70, we'll work out how much extra the halogens, 18 halogens, would cost compared to just the one LED. So those halogens would cost £23.40 more compared to one LED, and that means that they would both last 36,000 hours. So that's easily enough to get 6 marks. Next question. The picture shows an electric cooker hob. The simplified circuit diagram shows how the 4 heating elements connect to the mains electricity supply. The heating elements are identical. So here's the heating elements. 1, 2, 3, 4, they're all identical. When all 4 heating elements are switched on at full power, the hob draws a current of 26 amps from the 230 volts main supply. So coming down here would be 26 amps is what they're saying. Calculate the resistance of one heating element when the hob is switched on at full power. Give the correct equation. So how much current there is determined by how much resistance there is in the circuit, and obviously how much voltage there is. So we've got 230 volts. Now these are all connected in parallel with the mains electricity supply. So each one of these heating elements is going to get 230 volts. However, each heating element is not going to get 26 amps because that 26 amps is going to split up into 4 equal amounts. How do I know it's equal? Well, because it said that the heating elements are identical. So if they're an identical resistance, it means they're going to get an identical amount of current. So if I do 26 amps divided by 4, that's going to be 6.5 amps in each branch. Kirchhoff's law says what goes into a junction, 26 amps, must come out, and it's going to come out equally in 4 different parts. So now the equation we know is V equals I times by R. That's Ohm's law. We need to rearrange that. So therefore R equals V over I. They're in parallel, so each one is going to get 230 volts and they're going to get 6.5 amps. So that's 35.38 ohms. And they want it to 2 significant figures, so that's just 35 to 2 significant figures. Next part, the table gives the maximum current that can safely pass through copper wires of different cross-sectional areas. So that's how wide these are. So cross-sectional area, imagine here's the wire coming down, that's a thin wire. This one's getting thicker, this one's getting thicker, and this one is the thickest. That's what the cross-sectional area means. And that's the maximum safe amount of amps each of those wires can take. The power sockets in a home are wired to the mains electricity supply using cables containing 2.5mm squared copper cables. That means them ones. So that means the maximum safe amount of current is 20 amps. Most electrical appliances are connected to the mains electricity supply by plugging them into a standard power socket. It would not be safe to connect the electric cooker hob to the mains electricity supply by plugging it into a standard power socket. Why is that? Well, it told us before that there was 26 amps going to come out, and a 2.5mm squared cable can only safely take 20 amps. So it wouldn't be safe to use the 2.5mm squared. Describe the structure of the cable that should be used to connect the electric cooker hob to the mains electricity supply. So what you're looking for is the big cable on the outside. You'd need an earth, you'd need a live, and you'd need a neutral. And they should all have their own individual insulations. So outer cable should be plastic insulation. 3 inner cables or wires, earth, live, neutral, should also be insulated. So I've let them know what wires I expect to be in there, and I expect them to be insulated. So I could say insulation and insulation on that bit there. Mains electricity is an alternating current supply, so that's AC. Battery supply a DC, direct. What is the difference between an alternating current and a direct current? Well, alternating current, the electrons alternate backwards and forwards. Many times per second. DC current, electrons or current flows in the same direction. One way around the circuit, you might want to say. Figure 1 shows a slide in a children's playground. A child of mass 18 kilograms goes down the slide. The vertical distance from the top to the bottom of the slide is 2.5 meters. Calculate the decrease in gravitational potential energy of the child sliding from the top to the bottom of the slide. Gravitational field strengths that. Use the correct equation. Well, this is actually a paper 1 question now, but the rest of the questions are paper 2. So I'll just do this. Gravitational potential energy equals mass times by gravity times by height. So change in GPE, that would be the change in the height. So that's mass of the child was 18 kilograms, gravity was 10 newtons per kilogram, and the distance that the child changed was 2.5 meters. And that comes out as 450 joules. Like I say, that was on paper 1 though this year, 2019. So don't worry about that. But these bits are relevant. The slide is made of plastic. The child becomes electrically charged when he goes down the slide. Can you explain why? It's always the same answers. Friction causes electrons to be transferred. I'll actually get you 2 marks. If they want to say friction, you could say between the child's clothing and the slide. But that's often not necessary. So you get 1 mark for saying friction, 1 mark for saying causes electrons to be transferred. Going down the slide causes the child's hair to stand on end. What conclusion about the electrical charge on the child's hair can be made from this observation? The electric charge must be the same. Give a reason for your answer. Well, the hair is repelling. Like charges repel. Again, it's a standard question and a standard answer. Why would the child not become electrically charged if the slide was made from metal? Well, metal's a conductor, so the charge wouldn't build up. It would leak away to earth. And that's how to take care of business. Good luck with your paper too. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much and bye for now.